Okay, this is going to be a basic problem here involving friction and work. So here is an 8 kilogram box, and it's being pulled by a force of 100 newtons at an angle of 30 degrees. Coefficient of friction is 0.6. So questions we're going to answer here are, what is the work done by this force? What's the work done by friction? What's the net work? And what's the final velocity? So sometimes in these work problems, we end up needing to draw a free body diagram again. So let's just go ahead and do that. So we're going to have mg going down. We're going to have this force going this way. We're going to have a normal force going up. And we're going to have a friction force going this way. Good. And if we wanted to, we could break down this force into x and y components. Actually, it's not that we want to, we need to. This is going to be, here's our angle. A lot of times in work problems, they call this an angle phi instead of theta, so I'll just do that. So this is going to be f times the sine of the angle, and this is going to be f times the cosine of the angle. Oops, I drew the wrong angle thing again. See if I can get things to focus a little bit better here. Okay, that's a little bit better focused. Okay, so let's figure out the work that's done by the force. And our basic formula for work is going to be, I'll just leave it in vectors forms, force times the distance, or maybe they put a d here instead of an x. And that's going to be magnitude of f times the magnitude of the distance times the cosine of the angle between them. So for us, here's this force right here, that's 100 newtons. Oh, sorry, I forgot to say that the distance is going to go, let's make it 20 meters. That's going to be important to do there. Okay, so then this problem becomes pretty easy. We just have 100 newtons times 20 meters times the cosine of the angle between them, and I worked it out in advance, and that turns out to be 732, and joules is going to be the units for this since it's work. Great, okay, let's talk about the work that's done by friction. So same formula, we need to have work, move this up a little bit, is the friction force times the distance times the cosine of the angle between them. What we can see though is that the angle between friction and the distance is really 180. So that's just going to give us a factor of -1 inside this equation down here. So we'll just remember that it's going to be a negative work because the distance is this way and friction is acting in the opposite direction. So it'll be a negative work. What we do need to figure out though is what is this force of friction in terms of all this other stuff over here. So let's take a moment to figure that one out. What we have is normal force and this f sine of the angle going up and then mg going down. So if I want to figure out, first of all, let's just remember that the friction force is mu times the normal force. And I want to figure out what the normal force is. The normal force is going to be the difference between mg and this f sine of phi up here. So this whole thing's going to turn to mu times mg minus f sine of phi. And that's what the normal force is going to be. So it's this plus this equals this. This is going up, and it's got to balance that one going down. Good, so now I can just kind of take this and put it in for there, and then put in my distance right there. And remember, this whole thing's just going to turn into negative since it's a cosine of 180 degrees. So just putting in the numbers, there's my negative sign. My force of friction is going to be mu 0.6 times mg, 8 times 9.8 minus f, which is 100, and then we have the sine of the angle, which was 30. So I got to close that one up, and then times my distance right here, which is times 20. So I did all that math previously, and this turns out to be a work of -341 joules. And it's going to be impossible for friction to do more work than the force. Actually, that's not totally true. I should have also stated up here that our initial velocity is 0. Okay, so that's just going to come into the final velocity. So let's just say the initial velocity is 0. And if the initial velocity is 0, there's no way that friction is going to do more work than the pulling force. If my initial velocity was greater than 0, then it's possible that friction could do more work than the pulling force, and the whole thing would just slow down. So in this case, since it starts from 0, there's no way that friction can do more work than the pulling force. Otherwise, it would end up with a speed in the other direction, right? Somehow it would end up going this way, which can't really happen. Okay, so the network down here, I just have to add up this and this. And since this one's negative, it's going to be subtracted. So it's 1732 joules minus 341 joules, and that is 1391 joules. So that's my network. Now to figure out my final velocity. So my final velocity, you remember our work kinetic energy theorem. Work, or network, is going to be the change in kinetic energy. That's going to be 1/2 mv final squared minus 1/2 mv initial squared. And since my initial velocity is 0, I can just cancel that one out. So my network over here, 1391 joules, is going to be 1/2 mass, 8 kilograms. Let's see, 8 kilograms up there. 8 times Vf squared. And then I worked all this out, and my final velocity here is 18.6 meters per second, which seems reasonable, right? By the way, another way we could figure out the final velocity is if we just do velocity is acceleration times time. Don't really have the time, that would be a pain. I could also do v squared is v final squared is v initial squared plus 2 times acceleration times the change in position. And I would have to figure out the acceleration, which isn't really a problem because I have the force, and I could do acceleration is force over mass, and I could stick it in down here. And it's, in some ways, if you see how this is going, it's kind of like doing this step and this step kind of combined into one sort of thing over here. See how I had this mass that was going to get divided out onto this side, and there's your mass that's getting divided out onto this side. There's my factor of 2, which got multiplied over there. There's my factor of 2. And so this is sort of like your distance, and then your force times your distance. So it all works out. I like to use energy as well. It's just a nice tool to have in your toolbox. Okay, so there's a nice quick